The goal of exercise 2 in chapter 8 is to implement the full algorithm that I described earlier in this chapter. Now, in practice, when you're actually implementing linear algebra, you generally, not generally, you never want to implement that algorithm because it's tedious, it's long, it's computationally expensive. It involves explicitly computing the determinant of a matrix, which is not a very reliable and numerically stable algorithm for large matrices or matrices that are kind of close to being singular. So in practice, you're going to use the function inf or use other numerical methods that do not explicitly require the inverse. Nonetheless, the matrix inverse is a really important concept in linear algebra. And so translating a description of that algorithm into code is really useful from an educational perspective. This is the kind of thing that you do once, you're proud of yourself for doing it, and then in reality, you use the much more efficient numerical implementations that are provided with NumPy. So here is the description of that algorithm for inverting any square full rank matrix. You can see I describe here the different matrices that you need to compute. And in order to compute these matrices, you need to create submatrices that are created from the original matrix by blanking out or by ignoring individual columns and rows. Okay, and then computing the determinant of those submatrices, creating the grid matrix, and so on. Now, there's a lot of stuff going on here. There's many steps to do. And yeah, again, I think this is really useful from an educational perspective. And the goal here of this exercise is basically to implement this algorithm and compute a figure or display a figure that looks something like this. So now I'll switch to Python and I'll walk you through not only the steps that are involved here, but also I'll point out some of the tricky parts where you're likely to make mistakes. Here we start with a random matrix, so highly likely to be an invertible matrix. Okay, and then here I start by initializing some of the matrices that we need along the way to compute the inverse. Here I'm looping over the M and M. So these are, you can think of these as being the rows or the columns, or you can think of one loop as the rows and the other loop as the columns. And these are to blank out the matrices. So what I'm doing here is creating a vector of all trues. So it's true, and then however many rows there are in the matrix, and however many columns there are in the matrix. And then I'm sending one of those elements to be false. Okay, and then here you can see this is where we compute the minors matrix, or where we are populating each element of the minors matrix. It is the determinant that comes from the sub-matrix that is defined by all the rows and all the columns, except for the current row and the current column. Okay, and then here I compute the grid matrix. And here, this is another kind of tricky point where people are likely to make mistakes, in particular with the order of operations. So you might think of writing out a piece of code that looks like this. This initially looks correct, but what Python is actually going to do is associate the power with the number separately from the negative sign. So in fact, what Python will implement is this: 1 to the power of I plus j, and this is always going to be 1, right? 1 to any power is 1. And then minus that. So basically, this is always going to be minus 1. Okay, so you just need to make sure to associate the minus sign with the 1, and then exponentiate the term minus 1. And the parentheses help us do that. Okay, cofactors matrix, that's defined by the Hadamard multiplication. And then we have the adjugate matrix, which is just the transpose of the cofactors matrix, element-wise scaled by, or division by, the determinant of the entire original matrix. Okay, so this is that full algorithm. And then here, this is the inverse just using the NumPy function .inv. Of course, in practice, you never implement all of this stuff. It's totally insane. It's amazing for educational purposes. But in practice, you just use linalg.in. Okay, so we can run this and confirm that we get a matrix of zeros, indicating that the algorithm we implemented is correct. And then here I'm plotting them. I think this plotting code is not terribly interesting. I'm basically just calling IAMShow lots and lots of times. And that produces this matrix that I showed in the book.